Hi, my name is Bello. I'm an aspiring research engineer, and this is my video entry for the Cohere Lab Scholars Program. I'll be talking about the paper from tools to teammates evaluating LLMs in multi session coding interactions. Here, I'll be going in depth into the paper to talk about memory code, which is a benchmark introduced by this paper. It basically is used to test how well models can carry rules across sessions, handling updates or contradictions to those rules. It's actually a really simple structured test. You're a new developer, you've just joined the code base and you've been attached to a mentor. Over several weeks, your mentor casually has conversations with you, mentioning coding standards during your daily chats, things like all function names should end with like an underscore. And then it's also mixed with simple stuff like conversation about the weather, conversations about project deadlines, and other things which will serve as chatter or filler text. The benchmark specifically tests prospective memory, which is the ability to remember to do something in the future without explicitly being told to do so. This is harder than simple information retrieval because the model has to spontaneously recognize when to apply these previously learned rules or instructions. So, an instruction like all functions should start with an underscore has to be remembered and reused in the future on programming tasks. How exactly does memory code work? To understand how a model behaves in this context, the paper defines three evaluation setups. The first is to pass the model a single isolated instruction and a coding task. The baseline is to measure can the model follow a clear direct instruction. The second one is now to pass the model an entire session of conversations, multiple rules plus filler chatter. The challenge is extracting the right rules from a natural multi-turn conversation. And then finally, the hardest setup is that the model is fed an entire dialogue of history across multiple sessions. To succeed, the model must remember which rules are current, which rules are outdated ones, and then also know to apply them correctly during coding. These benchmarks on today's models shows that on simple setups the models do great, but as the number of sessions increase and as the number of revisions to instructions increase, the models, even the best ones, experience a great drop off in terms of accuracy. Now, why does this happen? The first thing to do was to rule out the hypothesis that this drop in accuracy was caused by the information retrieval problem. The authors did this by handling the model, the extracted instructions directly, cleanly, and summarized without distractions. And this still led to great drops in accuracy as soon as multiple sessions and instructions and updates were involved, showing that even though models have the right instructions, they still struggle to integrate and apply it consistently over longer periods. This points to a deeper problem at the heart of the transformer architecture, which, unlike its predecessors, the LSTMs and recurrent neural networks that maintain the running memory, transformers are based on self attention, which looks at all the words in a sequence at once. And this parallelism is a good thing. It made it possible to train bigger, more powerful models. But this means that transformers are inherently stateless and they don't remember anything between turns. Tools like Claude Code try to work around this by using an external file called a claude.md file to store important instructions, but it's basically just a band-aid on a fundamental limitation. And because of this, that's because these models don't have any evolving internal memory. The context files are just going to keep growing bigger and larger, and then they will consume the entire context window. A way I think of furthering the experiment or the research done in this paper would be to test memory code on models based on non-transformer architectures like Coastal Mamba, which is built on the Mamba selective state space model. Unlike transformers, which reprocess long context with like quadratic attention, Mamba performs linear time inference and maintains an internal state across the sequence. In practice, that means fast memory efficient processing with strong performance on long inputs, especially the situations where memory code becomes challenging for traditional models. If memory code's failures are tied to attention architectures, then a state space model like Mamba, designed to actually have internal state, should see a slower degrade in accuracy with longer sessions. In other words, better instruction tracking across many sections.